Hi, my name is Gene Schrader, and this is a video course on stepper motors and robot kinematics, theory and practice on STM32. There are 5 videos, including this one, and the total run time is a little less than 2 hours. Now, driving stepper motors is a common function for embedded systems. However, robot kinematics and trajectory planning is straying a little bit for an embedded systems course. But I wanted to do something fun with the stepper motors, and I've had a little exposure to kinematics when I worked for a robotics company many years ago. Now, in those days, our robots looked like this plastic model, of course much bigger, and if you know about industrial robots, the color of this one will give away who I worked for. Now, the robotic project for this course is a planar two-jointed arm, and it simply draws on paper. It might not be super exciting, but I chose it because it was cheap and easy to build, and it clearly demonstrates some principles of robot kinematics. So here is an outline of this first video. It contains the course objectives and content, the hardware and software I used, the hardware connections to the stepper motors, an overview of the demo and software structure, and then finally course notes like the GitHub repos. So here are the course objectives and content. I'll go through this briefly. So starting with the course objectives, we'll learn about stepper motors and how they work. We'll learn about designing a stepper motor software driver that operates using interrupts. In this case, it's for an STM32 MCU. We'll learn about the basic principles of robotic kinematics and trajectory planning. We'll learn about designing software to drive a simple planar two-joint robot for drawing. Now we want production quality implementation. Now the physical drawing robot that I built is quite crude and very far from production quality. So here I'm talking about the software, and it includes the following. We'll have written requirements and design notes. We'll have software modules that conform to a superloop architecture and that can coexist with modules performing other possibly unrelated functions. And we'll have software modules that provide debug and test capabilities. So the content of this course is mainly the theory and practice of the topics that I just went over. And we'll have some demos using the stepper motors and the robot drawing machine I built. At the end of some of the video lessons, I present some prompts or questions for you to think about, after which I give my take on them. This course is a continuation of my YouTube course with this long title that you can read. That introductory course covered getting started with embedded and using STM32 in the IDE. It also included the development of a software infrastructure layer based on the superloop and module pattern. There's a link to that course in the notes for this video. So in this course, I used the same module API that was defined in that base course. This makes it trivial to integrate the new code in this course into the base software. I also used some of the infrastructure modules that were developed in that base course, like timers and consoles. This is just normal layering and reuse of software. So the prerequisites for this course are that base course or a similar level of knowledge of MCUs and embedded programming. And we'll be looking at quite a bit of C code, so knowledge of C is a prerequisite. I would say this code in this course is similar to what you would see in industry, so if you want to improve your knowledge of C, this would be good code to read and understand. Now, kinematics is very mathematical. For the simple course project, it's not too complex, but it involves trigonometry and algebra. However, a full understanding of the math is not really necessary. What is important is to understand the concepts. And we won't be doing any derivations or anything, although we will be looking at implementation of these equations in C. Finally, not much knowledge of electronics is needed, but some basic knowledge of things like voltage and current would be helpful. Here I'll tell you about the hardware and software used in developing this course. As always, my setup looks a little messy with all of these jumper wires, but it works. And you can see here is the first motor controlling this first arm. And then at the end of that arm, there is a second motor which controls this arm. And then at the end of that arm is the pen that does the drawing. So there is an ST Nucleo board called Nucleo F401RE, and it has an MCU with the same name. Then there are two inexpensive stepper motors. This is the model number. Each stepper motor has a hardware driver board. And the driver boards are needed because a GPIO pin on an MCU doesn't provide enough power for a stepper motor. So the driver board just increases the power of these GPIO signals. One of the spare motors is here with this cable, and then this is what the driver boards look like. Now this stepper motor here, and again here's the model number, is available in many places like Amazon and eBay, and they are cheap. I think I got 5 of them for $11, including shipping. Now when you spend roughly $2 for a motor and a driver board, including shipping, you can't expect a lot. But I think they're actually pretty good for the price. For my application to work well, this drawing robot, I need better stepper motors than these. But it works okay. It's not great, and you'll see it in the demos. Of course, there are other various bits of metal and screws that I use to construct this machine. And I have some more detailed pictures of the construction in a later lesson. There's also a 5-volt external power supply that I used, but I'm not sure if it's really needed. I'll talk about that in just a bit. In terms of software, everything I used was free, and you can look at this list. Now, I don't actually show the IDE in any of the lessons, I don't think, but of course I use it to compile the code and load it on the MCU. And I use the IDE debugger when I was writing this code. Now, this last point is about infrastructure software that actually runs on the MCU. If you wanted to exactly duplicate what I did, you would need to include this software. And there's a GitHub repo for this course, which I'll show you in just a bit. Here I show the connections between the MCU Nucleo board and the stepper motors. I have 4 GPIOs for each motor connected to the driver board. I also supply 5 volts and ground from the Nucleo board. You can see how the GPIO signals pass through the driver board to the motors. This blue box represents the driver chip, and the white box represents a connector on the board that the motors plug into. Now, the Nucleo board also supports ST-Link, which is the programming and debug interface. It plugs into my laptop via a USB, and that's how it gets its power. ST-Link also carries the console serial connection. Now in this slide you can see where I supply the power for the motors from an external supply rather than from the Nucleo board, which gets its power from the USB cable on my laptop. I thought I was having issues with motors slipping steps, and I'll describe what that means in the next lesson. Anyhow, I thought that the Nucleo board perhaps could not supply enough power, so I added this external supply. Frankly, I was changing a lot of things at the time, and I'm not really sure I was slipping steps, so I'm not sure that this power supply is really needed, but I just left it in there. Before I get into the real lessons, I wanted to talk about the overall demo design to give you a big picture of where we're headed. As I've mentioned, the course project is a simple 2-joint planar robot for drawing. Now, my overall software architecture from my base course on embedded is a super loop and software modules. So for this course, I created 2 new software modules. A step module that controls a single stepper motor using steps as units, and a draw module to simultaneously control 2 stepper motors in a coordinated way to draw from point to point on a Cartesian plane. I also enhanced some existing modules, one for timers and one for discrete I/O, which we normally call GPIO. The enhancements were to make setting GPIO outputs for the stepper motors fast and precisely on time. I'm not sure if these enhancements were necessary, but I just wanted to be certain. Here is a diagram showing how these different software modules interact with each other. At the top we have the draw module, which coordinates the motion of the pen, which is at the end of the second arm. The module has some console commands that allow me to perform the motions for demos. Now the draw module gives stepper commands to the step modules, one for each motor. And that's the stepper commands. The draw module also gets information from the stepper motor, such as the number of steps per revolution. Now this note here is important. The draw module is doing complex motion calculations that can take some time, but it can work ahead on these calculations and queue up commands to the step modules. This avoids pauses in motion, and we'll see how that works in later lessons. Now the timer module is used by the step modules. The step modules use the timer callback to issue the new stepper GPIO signals at the right time. Finally, the DIO module actually outputs the GPIO signals. We'll be looking at the details of the operation of this in later lessons, but this gives you the big picture. Now this diagram is busy and I won't go through it in any detail, but it shows all of the software contained in the MCU image, and I think it's often useful to be able to get the complete picture. So I'm just going to go through a few things here. First, everything above this purple line is code I wrote for this course and previous courses, and it's all in the GitHub repo for this course. Everything below this purple line is things like standard C libraries that came with the tool chain or code provided by the IDE, including some code generated by the IDE. Now at the very top we see the new modules developed for this course, Draw and Step. You can also see some of the infrastructure modules from previous courses that I'm reusing for this course. And by the way, the modules with this blue-gray background are ones that access the hardware using the STM32 low-level library. The modules with a yellow background do not directly access these libraries. Instead, they use APIs provided by the blue-gray modules. So these blue-gray modules are providing some hardware abstraction. And finally, this box here, this teal one, shows the module startup code and the super loop where all of the higher level modules are integrated. So here are some final notes before getting started with the lessons. First, YouTube does not allow you to easily update videos, so any corrections or clarifications to a video will be in a YouTube video comment for that video, and I'll pin it as the first comment. I'll also put that information in the description notes for the video. So there are two GitHub repos for this course. The first repo contains the source code, and this includes the code for the base course plus the work I did for this course. And there might be code for other follow-up courses in there as well. I do it this way because I want to leave the code for the base course unmodified so it matches up with the videos for that base course. The other repo is for course materials, which is mainly copies of external documents. And there's a README in there that describes the documents and where I got them from. So links to these GitHub repos are in the notes for this video. I'll also note that I did my work using Windows 10 as my development machine, but the tools like the IDE are meant to run on other platforms like Linux and Mac OS. So if you try this course, I'd be interested to hear what you think. Any questions or comments, just use any of the normal YouTube methods, mainly the video comments. So that's it for the introduction. In the first lesson, we will look at stepper motor theory of operation. Thanks for watching.